Ionic polymerization. The ionic mechanism of chain polymerization involves an attack on the pi electron pair of the monomer, as in case of free radical polymerization. This time, however, not by the unpaired electron of the free radical, but by either a positive or a negative ion. Well, imagine a system where a proton is introduced into a monomer. The proton now pulls the pi electron pair towards it, and the positive charge of the proton is transferred to the farther end of the monomer molecule, forming a carbonium ion. Carbonium ion is positive. It will be noticed that in this process a sigma bond is formed between the proton and the monomer unit, and the polymer chain growth is initiated. This is represented as follows: proton, monomer, pi electron pair getting attacked by the proton, forming a sigma bond which is represented by CH3, and then the proton is transferred to the farther end of the molecule. Carbonium ion C+ attacks the pi electron pair of the second monomer molecule and pulls it over. The positive charge is transferred to the farther end of the second monomer unit. Thus, now the chain is propagating. The chain reaction sets in. In this chain reaction, however, no divorce of the electron pair takes place, but only a displacement of the pair as a whole and the formation of a carbonium ion. So in earlier case there was a divorce, one going here, one going here, but in this case the entire thing, the entire pair is going displacement, getting displaced, and there is a formation of a carbonium ion. So CH3 CHX getting attached to this CH2. So instead of here, this entire pair is going here. Okay, that is the displacement. And the carbonium ion. Carbonium. Okay, carbonium. If there is a O, it is positive. Okay, remember like that. Strong Lewis acids such as boron trifluoride, generally called the catalyst in ionic polymerization, in the presence of small amounts of water or methadone, known as co-catalysts, form hydrates which exist as ion pairs. So now this boron trifluoride plus water, catalyst plus co-catalyst system, giving this ions, ion pairs. Why they are ion pairs? Because they consist of both H plus and F3BOH minus ions, where H plus is the initiating cationic species. Cations are positive, and F3BOH minus is the counter ion. The H plus proton now attacks the pi electron pair of the monomer, starts the chain growth through the carbonium ion, and F3BOH minus an ion faces the growing chain end because it is the counter ion, right? Okay. This step constitutes the initiation step of the polymerization. The propagation reaction involves further adding up the monomer units and simultaneous transfer of the charge to a newly added monomer unit. So this what you got, then again a fresh monomer species added, then again there is a displacement of the pair as a whole, and this gets into a sigma bond, and this is transferred to the farther end of the molecule along with the counter ion F3BOH. Then the propagation is further and you get three molecules. The chain is set in. As more and more monomer units are added up, the chain keeps on growing, and in doing so, the pi electron pairs of the monomer unit are pulled in the direction opposite to the growth of the chain. Because here, right, they are pulled here. So it is not in the direction of the growing polymer chain. It is pulled backwards. Also, the C plus ion keeps on moving in the direction of the chain growth, and the C plus ions keep on going to the farther end of the monomer molecule. That is in the direction of the chain growth. And the counter ion all the time moves along, and the counter ion all the time moves along with the C plus ion like a watchdog. Termination occurs when a collision between the growing C plus ion and an anion, either from the counter ion of another growing chain or from some deliberately added anion takes place. The possible reaction that takes place during termination involves the following two factors. Number one, donation of a proton to the counter ion, which is in fact the reversal of the initiation step, resulting in formation of a double bond at the end of the growing polymer molecule and the resultant arrest of the chain growth. So donation of a proton to the counter ion. So this is the growing polymer chain, and you have donated a proton to this counter ion, and this H is gone here, F3BOH, so therefore this gets stabilized and gets separated, and this forms a double bond to the dead polymer molecule. This process of donation of a proton and reformation of the BF3 hydrate, BF3 hydrate means BF3 plus water molecule, is called ion pair precipitation. So termination by ion pair precipitation. Now formation of a covalent bond between carbonium ion and the counter ion. When the termination occurs by simple coupling, so there is a covalent bond formation between the carbonium ion and counter ion. So this is the carbonium ion plus sign. Okay, and now there is a covalent bond formation between them. So BF3 is separated and this OH is added as a covalent bond here. So also the four valencies of the carbon is satisfied, so this gets as a dead polymer. In both the cases, however, regeneration of the initiator takes place, because here we get BF3 and in that case we get BF3 hydrate. However, regeneration of the initiator takes place. This type of polymerization, where the initiation is done by a proton and the propagation is carried out by a carbonium ion, is called cationic polymerization. The initiator used for this purpose in addition to BF3 include AlCl3, SnCl4, TiCl4, aluminum trichloride, titanium tetrachloride. Okay. Examples of monomers that can undergo cationic polymerization are isobutylene, styrene, methylstyrene, and many mineral ethers. There is another type of ionic polymerization called anionic polymerization, where the attack on the pi electron pair of the monomer is done by a negatively charged ion, such as an anion. Such a system has extra electrons, and the resultant negative charge attacks the pi electron pair, pushing it farther away as possible, that is, to the end of the molecule. At the same time, it forms a sigma bond with the monomer molecule. The electron pair push to the end of the molecule results in the formation of carbanion. So here instead of O there is A. So an EM, carbonium, this is carbanion. So you see you have to remember that carbonium is positive and carbanion is negative. So here simply this negatively charged anion attacks the pi electron pair of the monomer. Itself forms a sigma bond and the farther end of the group we get the negative charge. Thus carbanion thus formed now propagates the chain growth by attacking second monomer unit, pushing the pi electron pair farther to the end and forming a sigma bond with the new monomer unit like this. Okay. Same thing is happening, displacement of the pi electron pair as whole. From here it goes to here, opposite to the direction of the growing chain, and this carbanion goes to the direction of the growing chain. So again added and they are simply continuing. Therefore in the lastly we have represented it as n times. There are n number of repeating units. So we have again in cationic polymerization an electron pair displacement process. As in cationic polymerization, this is as an electron pair displacement process, where the strongly negative anion pushes the pi electron pair of the monomer double bond down to sigma level. The difference between the cationic and the anionic process is that in the former case, the moment of the electron pair is in the direction opposite to that of the chain growth, whereas in the latter case, it is in the direction same as that of the chain growth. So I was wrong. So this is in the direction same as that of the chain growth because CH2, this bond is forming, and yeah, CH2 and this C, it is opposite in the direction opposite here. CH2, CHX, CH2, CHX. So here the difference between the cationic and the anionic process is that in the former case the moment of the electron pair is in the direction opposite to that of the chain growth, whereas the later case is in the same direction of the chain growth. Of course, the anionic process also the ion pair exists with a positively charged counter ion always running along in the direction of the chain growth close to the carbon ion. The general type of initiator used in this case are organoalkyl compounds such as butyl lithium, triphenyl methyl potassium, methyl sodium. Alkali metal amides can be used for anionic polymerization as well. Monomer capable of undergoing anionic polymerization include butadiene, isoprene, styrene, and acrylonitrile. The termination in anionic polymerization is, however, not usually a spontaneous process, and unless some impurities are present or some strongly anionic substances are added deliberately, invariably no termination occurs. Thus, if the polymerization is carried out under controlled conditions and the impurities are avoided, the reaction proceeds till all the monomer is consumed. In this case, while there is no monomer left to be polymerized, the carbon ion at the chain ends remain potentially active. What this means is that if a fresh quantity of monomer is added to the polymerization the polymerization again goes on until all the freshly added monomer is consumed. Again, the chain ends are like a gasping tiger, ready to drink away any monomer blood that may be supplied. Studies have shown that polymerization can be restarted in this manner even after weeks by adding fresh monomer. It is as if the polymer is a living entity, and in fact, the polymer produced by these techniques are called living polymers. They are alive and they keep on growing as long as we supply fresh quantities of monomer. Just as many of the living organisms grow, as long as food is available. The living polymerization technique is useful for many applications. Block copolymers, for example, is prepared by employing this technique. So now everything is clear between cationic and anionic polymerization, but only doubt I have is how he's saying that the difference between cationic and anionic process is that the former case, the moment of the electron pair is in the direction opposite to that of the chain growth, whereas in the later case, it is in the same direction as that of the chain growth. So here what is happening is like this electron pair is forming bond with this. So it is in the direction opposite, but it was happening in this case also. So let us see. The electron pair is at the same time it forms a sigma bond with the monomer molecule. Okay, so this is forming a sigma bond with this one. Okay, molecule. The electron pair is pushed to the end of the molecule, resulting in the formation of carbon ion. Okay, so this electron pair is pushed here. Okay, now I got it, the difference. So in that case of cationic polymerization, this electron pair was going here and forming the sigma bond. But here this anion itself is forming the sigma bond with the freshly added monomer, and the pi electron pair of the monomer is going to the farther end and forming a carbon ion. So that's why he said in this case there is excess of electrons. As you can see, such a system has an extra electron, and the resultant negative charge attacks the pi electron pair, pushing it as farther away as possible, that is to the end of the molecule. At the same time it forms a sigma bond with another one. So now the doubt is clear. What is the difference between cationic and anionic? So just keep this in mind. Read it again and again, you'll get it. Here in this case, this was going to the farther end, this was coming backwards. Okay, so this direction of arrows will clear your doubts. Okay, I hope you get it. Then your cationic and anionic polymerization is done. Cationic polymerization and anionic polymerization.